network of professionals in the field of electron devices. And what we have is a group of experts that is working. This is a free job that we do this just voluntarily. We take many different activities and organize many different conferences, awards, etc. We have regional chapters all around the world, which are associations that organize this kind of activities, as most of you know. So here you see some of the conferences that we organize, including the International Electron Devices Meeting, which is the flagship conference for devices, and also the VLSI conference, among many others, as well as many, we have a lot of humanitarian projects to promote electron devices, science and technology all around the world. And this is one example of excellent speakers for some of our webinars. And here you can also see more pictures about some of the activities that we develop. So I think this is just a brief note before my technical talk to let you know about these activities done. It's not the purpose is not a kind of commercial thing, because the subscription to these activities or to this society is very cheap, and participating in the activities is one of the things that has given me most progress in my career, to make connections, so and also to present my work. So I encourage everybody to check the website of EDS and to try to learn more about this society.
No, it better. Why I am not okay.
So here I would like to start with my
कुछ तो करो
technical presentation. Yes.
Yes, Professor, just wait, please. Yeah, Vishwasara, please unmute it. Oh, I request to.
Sorry, I cannot hear.
Hello, Professor Lanza.
Yes, can you hear? Yes, can you hear me?
No. Actually, one of the participants is unmute yourself and they are speaking actually, so that's why I'm stopping him actually, not you. So please continue.
Okay, thank you. So the title of my presentation is Hexagonal Boron Nitride-based Memristors for True Random Number Generation. Before starting, I would like to thank all the members of my group who are doing a lot of experiments and simulations. Actually, now our work covers from atoms to systems, so we have people with different expertise. And I hope I can put more people in my group. I can put one, at least. I'm interested on bringing at least one member from India. So I will be in this conference in India soon, in Bangalore, in December. So I hope to meet people from the community there and try to establish more connections, collaborations, and bring people to my team. This is the outline of my presentation. First, I will introduce 2D materials in the semiconductor industry. Then I will talk about local defects in chemical vapor deposited hexagonal boron nitride. And finally, I will show you one type of circuits that we are doing with this material. So if you take a look to the semiconductors industry, you can see that new materials have been always studied. Okay, the first transistors were made of germanium, then silicon was employed for economic reasons. The material for the contacts has been also changed from gold to interconnections made of copper, aluminum, and contacts made of titanium nitride. And for the insulators also, silicon oxide was the preferred insulator for silicon transistors, but then now the transistors are using hafnium dioxide. So new materials are always being employed, and recently in 2004, one new type of materials called two-dimensional materials was discovered in Manchester, and after that many wonder properties have been discovered, such as high conductivity, high thermal conductivity, high mechanical strength, flexibility, transparency, etc. From the very beginning, academics have claimed that these materials could have an impact in the semiconductors industry and improve integrated circuits. And they were mostly ignored by the industry for many years because many of them exaggerate a lot. When you exaggerate, then people don't trust you. However, a few years ago, the industry has started to investigate seriously these materials. And some things have started to come out. Two-dimensional materials are already being employed in some commercial products, such as sensors from the company Graphenia, or some specialty cameras, such as these ones from the company Emberion, which have some graphene. So the integration of two-dimensional materials at the back end of line of microchips is already a reality, although it is very reduced still, because there are many integration challenges, as I will explain. However, it is expected that they reach transistors and other high integration density neuromorphic computing systems. Here you can find one timeline presented by IMEC in IDM 2020, in which they propose the use of two-dimensional materials as a channel in the front end of line fabrication of transistors. Actually, if you check the International Roadmap for Devices and Systems from 2016, there was no discussion at all about 2D materials. But in 2017, it was the first time these materials were proposed as channeling field effect transistors, and it was stated that this will happen by 2024. And in the IRDS of 2020, this date was delayed until 2028 because several integration problems appeared. So this means that still the industry believes on this technological solution. However, it is difficult, so the date was delayed. Also, it was expanded, this prediction, to beyond CMOS devices. Here, let me show you a little bit about two-dimensional materials. Okay, so the first time a two-dimensional material was isolated was in 2004, and it was graphene. It was just the authors take a piece of graphite and they take some Scotch tape and peel this kind of graphite sample, like powder, into small flakes by repeated peeling. And then what they get is something like this, you know. This is a small flake of few micrometers that contains multiple thickness fluctuations and is very small. So with this thing, you cannot fabricate a wafer of two-dimensional materials. It's impossible. However, this was used for some exploratory studies to analyze the properties of the material itself. And actually, using this method, you can see that the crystallographic structure of the material is nearly perfect. It's very good. It's perfectly layered. So based on this, as I mentioned, multiple properties were discovered. However, as I mentioned, you cannot fabricate wafers with this. You cannot put it at the wafer scale. So in 2009, another work was developed in which the authors synthesized for the first time graphene by chemical vapor deposition. So basically, they use a tube furnace with a catalytic substrate, in this case copper, and they have a precursor containing the molecules of the material that they wanted to deposit. And they have a carrier gas. And then when you open the valves here at high temperature, some seeds are deposited on the catalytic substrate. The seeds contain molecules of the precursor of the material we want to grow. Then at high temperature starts to grow laterally until they merge and they form a continuous film. Okay, and in this way, if you have a very large substrate, you can grow the 2D material everywhere. Okay, and this is now compatible with the, I mean, this can reach a wafer scale growth. However, this material is not crystallographic perfect. Actually, it contains several defects, and these several defects are generated by many reasons. So here I put cross-sectional TEM images and one conductive atomic force microscope map, as well as one schematic to explain you what are the most common defects in 2D material. And I use multi-layer 2D material because it contains more defects, so you can have a global picture. The most common type of defect is thickness fluctuations. You also have lattice distortions. So this 2D lattice is distorted and you have few atoms wide amorphous regions. You can also have contaminants like polymers. You can also have wrinkles and gaps between the 2D material and the substrate. Okay, all these can alter the properties of the electronic device. You can also have twin boundaries, which is basically one layer that separates into two. You can also have grain boundaries, which is one of these seeds, that's two of these seeds that start to propagate laterally. They merge together and they form lattices that are not the same than inside the crystal. For example, if in the crystal we have an hexagonal lattice, then here we may create heptagonal, pentagonal. There are also missing bonds, and these are all defects affecting the electronic transport. Actually, this grain boundary that you see here, it is in a monolayer material. In a multi-layer material, normally they appear to be wider, something like this, but as lines, and actually is much easier to observe in the conductive atomic force microscope map. And also, of course, we have some regions within the CVD grown material that they look nearly perfect, okay, like you can see here. Here in this schematic, I show you the effect of these defects in the out-of-plane resistance. Okay, now let's consider we are using an insulating two-dimensional material that is multi-layer, such as multi-layer hexagonal boron nitride. If we deposit two electrodes and apply electrical voltage, the current, let's say the resistance, will change like this. Okay, the thicker areas will have higher resistance. The defects like lattice distortions, twin boundaries, and grain boundaries, they will reduce the out-of-plane resistance. The wrinkles, the gaps, and the insulating particles, they will increase the resistance. Moreover, there are not only native defects, but there are also another defects inherit or that are produced during the fabrication of the device. So let's see some of them. The first type is during the transfer process. The transfer process is necessary because the CVD growth is done at 1000 degrees. So you cannot grow this on a CMOS wafer with containing some circuits, or let's say transistors, because they will be damaged. So you need to grow the material in another different catalytic substrate and then use a transfer process. This transfer process is low temperature, so it's fine to end up transferring onto the CMOS wafer. But this process produces contaminants from a polymer scaffold necessary to transfer the material and from the catalytic substrate used for the growth, in this case copper. And also it produces cracks. The cracks can completely damage the material and destroy the devices, so reduce a lot the yield. Okay, actually, when we fabricate memristors made of monolayer hexagonal boron nitride, we see that 95% are shorted because we have some pinholes and cracks. While when we use multi-layer, these cracks can be avoided and pinholes, and we observe that the memristors switch properly and that around 98% work well. Another type of defects introduced in the 2D material is during metal evaporation, during metal deposition. Depending on the method that you use for the deposition of the material, you will be introducing defects. And depending on the type of this 2D material, depending on the energy to form vacancies, you will introduce also more or less defects. It has been observed that 2D semiconductors like molybdenum disulfide can be severely damaged when doing evaporation of gold. Boron nitride also get damaged. Here is a picture of a exfoliated boron nitride. Here is another exfoliated boron nitride after the evaporation of silver. If we deposit the silver by inkjet printing, which doesn't deliver high energy to the material, there is no damage. But by electron beam evaporator, which is one of the methods used in high integration density circuits, this produces some damage. Actually, we have also confirmed this by atomic scale simulations. If you are interested, you can check this article. Another source of defects is when trying to do selective etching to open contacts. For example, if we have one transistor that uses a 2D dielectric, and we have a gate dielectric that is boron nitride, we have to open the boron nitride to contact the 2D semiconductor. This can also generate defects in the form of roughness, and we are going to be changing the surface properties of the material. Layer by layer etching has been achieved. However, still the roughness of the sample is not as good as it should. So we need more progress on this. So when we have defects, doesn't matter if they are native or if they are generated during the transfer or during the opening of the contacts or during the metal evaporation, we are changing the energy states. Okay, we are changing the electrical properties of the material, in our case hexagonal boron nitride, which is insulator. So here you see an atomic scale calculation of multi-layer hexagonal boron nitride with perfect structure. We see a band gap around 6 electron volts. When we induce some defective states, we observe some states in the band gap. Okay, so these defects produce electronic states, and then the leakage current across this material can increase. We have also checked not only how is the electron transport, but also we have checked what is the energy to form defects. So here you can see we have a cross-sectional TM image of multi-layer hexagonal boron nitride grown by chemical vapor deposition, in which you can see some native defects. You see here. So we simulate this by atomic scale simulations and observe that the energy that you need to form a boron vacancy in this part of the material is around 10 electron volts. But if you calculate the same energy to form boron vacancies in this part of the material, which is simulated like this, the energy is much lower. And therefore, this means that it is going to be much easier to trigger ionic motion in this part, while this other is much more stable. Moreover, not only we calculate electron transport and formation of boron vacancies in the boron nitride. We also simulate what is the energy that we need to make a metallic atom penetrate into the material. Okay, when the material has perfect layer structure, you need a lot of energy to introduce one impurity inside it. And you can see it here. This is the energy that is necessary, around 15 electron volts. If this material has one little defect, like a boron vacancy or nitrogen vacancy, you see it can penetrate in the top layer, okay? It can penetrate the top layer much more easily, okay? And after that, it also reaches for the second layer, which has no defects, it reaches 15 electron volts. And if we have a material that is completely amorphous, the energy that we need to make this atom penetrate is much, much lower, okay? So I think this is very interesting because it shows that the native defects in the CVD grown multilayer hexagonal boron nitride have different electronic properties. We have done one experiment in the boron nitride that is very interesting. So we scan the surface of the boron nitride with a conductive atomic force microscope, and we observe several spots of the sample that are more conductive than others. Okay, these spots of the sample are these lattice distortions. Okay, this point will be this point. Okay, the green and red one. And it shows higher electrical current. We also do this for hafnium dioxide, and we observe also some points that show a little bit more current than others. Okay, and with this, we can observe that the hafnium oxide also have local defects that trigger out of plane current. So it's the same situation for boron nitride and for hafnium oxide. But here comes the difference. If you start to apply a sequence of current maps in the same spot, the one in hafnium dioxide will grow relatively fast until producing the dielectric breakdown, forming a filament and expanding laterally. Okay, you see that it expands laterally, and there is a sudden jump and triggers the breakdown. In the boron nitride, it doesn't happen like this. In the boron nitride, this filament grows laterally, but very, very, very few. This lateral increase is very small, and I need to apply many more current scans, which means that there is a confinement effect. This current can flow across this, but this doesn't expand, probably because this layer material is very stable, and this thing cannot propagate laterally. Okay, it just stays confined across this defect. This is a very interesting phenomenon that doesn't take place in amorphous metal oxides like hafnium oxide. Okay, so we have observed that across this path, you can produce two resistive states. You can form a filament of ions penetrating from one of the electrodes, and they sit here, and they trigger a low resistive state. But if we apply voltage of a different polarity, we can destroy this conductive filament and then generate a high resistive state. So with these two states, you can make memristors, and the memristors can be used as an electronic memory. Actually, this is not unique for 2D material. Actually, the memristors were first employed or were first made by metal oxides and phase change materials. But anyway, the memristive memories are a reality. They already occupy 0.5% of the standalone memory market, and there are several products that are commercially available. Okay, although the consolidation of this memory within the memory hierarchy will take time, and it will be good for some types of applications, and for others we will keep using traditional memories. Memristors exhibiting two different states can also be used as radio frequency switches. Okay, for this you need a very small value of low resistive state resistance. Here is named R on, because you need to allow the radio frequency wave to be transmitted. Okay, so you also need to have a suitable of capacitance in the high resistive state. But some studies have already used 2D materials to make radio frequency switches. You can study the works of Professor Deji Akimbande from University of Texas in Austin. And if we have memristors that exhibit multiple non-volatile states, not two, but multiple, then you could also fabricate crossbar arrays of memristors for vector matrix multiplication. The vector matrix multiplication, which looks like this, you have a vector and a matrix of memristors, and then you get an output vector, is one flagship operation used for neuromorphic computation and hardware integration of artificial neural networks. So these memristors could provide a solution for this type of applications. And then the memristors also exhibit one property which is unwanted for memory, radio frequency switch, and neuromorphic applications. This is called the variability. Cycle-to-cycle variability, like this, and device-to-device variability. This variability, as I mentioned, is bad for the other applications because you cannot recognize the state of the memristor if there is variability. However, it can also be exploited for hardware security, okay, especially for data encryption in the form of true random number generators. Okay, when you encrypt data, normally, or for some security applications, normally you use this kind of true random number generators. So actually, the true random number generators made of memristors consume low power, and they are suitable for, especially for the Internet of Things, because all these devices transmit information, and before transmitting the information, you need to codify it using true random number generators. One application that everybody is familiar is the one-time password that we receive in our telephones when we make online purchases. Our bank sends us this code to the telephone to validate the purchase. So this can also be done by exploiting the randomness of the memristors. And this is done by comparing with one reference value, and then if this value is the value that I read from the memristor, let's say the set voltage, if it is above one reference value, then I will generate 1, 1. If it is below, I will generate 1, 0. Then by producing strings of ones and zeros, I can produce numbers, like for example, this digit 44575. Another option is to generate IDs for objects. For example, if I have a crossbar array of memristors that switch between 5 and 5.5 volts in global, and I apply a pulse of 5.25 volts to all the devices, some of them they switch, some of them will not switch. And this, which ones will switch, depends on the atomic structure of the device, of the metal insulator metal junction. And it is impossible to predict which one will switch and which one will not switch. So this can be employed as a physical unclonable function for objects to identify objects. Okay, so say this, I would like to show you what we have done in my lab about multi-layer hexagonal boron nitride based through random number generators. Here you can see one example. We have a bottom electrode material on a silicon oxide wafer. This is made by electron beam evaporation. We also have electrodes with different size. You see, this is narrower, this is wider. Then we transfer a sheet of CVD ground hexagonal boron nitride, and finally we deposit the top electrode. Okay, when we deposit the top electrode in one specific part of this junction, we will have a metal boron nitride metal structure. This structure, this top electrode can be fabricated by electron beam evaporation and by other methods. In this case, we fabricate by inkjet printing of silver. Okay, this is the structure of our device, which looks typically one metal insulate metal HBN metal structure looks like this. Then now what we do is to apply a constant voltage to this junction between here and here, and measure the current across it with a high temporal resolution. For this high temporal resolution, we employ one custom-made preamplifier, okay, like this. This is done by one of my postdocs. And here is the memristor that is biased, okay? Okay, when we do this, we apply a constant voltage of 70 millivolts to this device, and this is what we measure. We measure a current signal that fluctuates between two different states. One is here, and the other one is here. Okay. You can see it better in this zoom-in image, okay? These transitions are completely random, okay? It is impossible to predict when the device will be in this current level and when it will be in this other level. We statistically analyze these current values, and we can clearly distinguish two states, okay? One peak here, which is very well defined, which is this one, and one peak here, which is the upper, which is not as evident, but still we can clearly detect two states. We also quantify the speed of the transitions. You can find it here, okay? We calculate the power consumption of this signal, and it is 5.25 nanowatts, okay? So generating generating fluctuations between two states at this power is something low, at least for this type of signal. This type of signal is called random telegraph noise, okay? This is when this signal fluctuates between two states randomly. The signal is not produced in similar structures made of exfoliated hexagonal boron nitride, okay? This type of sample, it just shows jumps, but not this kind of stable stochastic fluctuation, okay? This indicates that the stochastic signal the random telegraph noise signal is probably generated by the local defects inside the CVD grown boron nitride. This exfoliated boron nitride doesn't contain defects, doesn't show the signal. So we analyze with the conductive atomic force microscope if these defects exhibit this type of signal. We scan one sample, this is the topographic map, this is the current map, of polycrystalline hexagonal boron nitride on polycrystalline copper. We see this is the picture of the current. We see current at the copper grains and at the boron nitride grain boundaries. It is very obvious here, for example. And also we see current inside the grains. Inside these grains, we take a map, zoom in, we see this. There are many, many defects in the boron nitride, okay? But these defects are embedded inside the 2D layer structure and they are stable, okay? As I mentioned before with this confinement effect. If we put the tip of the conductive FM outside and we apply a constant voltage, this material layer is insulating, so there is no current, just electrical noise. But if we put the AFM tip inside one of these defects, we can clearly observe random telegraph noise signals. Okay, so basically this confirms in situ that the random telegraph noise signal that I observe in my device is produced by these native defects in the boron nitride. Okay, so what we do in our previous study is we take the boron nitride device, we apply a constant voltage, and the current signal produced, we input it in one circuit that looks like this. First, we have an IV converter, high-pass filter, and then a comparator, a toggle FF, and a sample on hold. And finally, a non-linear feedback shift register. And then here at the output, we can generate one string of bits like this. Okay. However, this output is a little bit slow. The number of bits that I can produce is a little bit slow. So what this non-linear feedback shift register does is to increase the throughput, and then we can get random signals that fluctuate at frequencies of 1 megabit per second. Okay, here you can see one string of bits. This string of bits fluctuates between 1 and 0. We have plotted them as a chessboard. Okay, and you can see that the position of these bits is random. Okay, it is randomly distributed. There is no pattern. Sometimes if the if the generation of numbers is not truly random, you see some patterns that repeat, but here there is no pattern that can be observed. Of course, doing this with your eyes is not something really accurate. So what we do is to do this, to run the randomness test from the National Institute of Standards and Technology from the United States. And we observe that we can pass all the randomness test, and the chessboard pass all the randomness test. Actually, this example that I'm showing here is not for the circuit that I have presented here. For this circuit, the randomness test list is shown in this article. Okay, the one that I have shown you corresponds to this other circuit. This is a similar true random number generator, but in this case, we didn't use a simulation. What you see here is that this circuit has been simulated using SPICE. Okay, in the next step, we go towards the full hardware implementation of this true random number generator. And we use a circuit that looks like this. We have a microcontroller from Arduino here, and we also connect some discrete devices, basically resistors and capacitors and operational amplifiers. Then we have the low noise transimpedance amplifier, which is connected to the boron nitride memristor, which is here. Okay. And then now, with this hardware implementation, again, we observe that there is no pattern and that we can pass off all the randomness tests. See what happens if we don't put any signal at the input of the nonlinear feedback shift register. We see a pattern here. You see? Here, there is a pattern. So this doesn't pass the randomness test, okay? So the randomness is being provided by the stochastic fluctuations of the current in the random telegraph noise signal produced by the memristor. Here, you can also see that with other types of noise, our circuit is also capable to produce true random number sequences. Okay, these are other signals that are not strictly random telegraph noise, but that can also result in one stochastic signal. However, I have to say that these other sources of these other signals are also produced by the memristor. Okay, if we don't put any signal on the input, as I mentioned, we don't get a true random number signal. Okay. Okay, so the next step in our work, what we are doing now is to, instead of having this Arduino in the proto board with this transimpedance amplifier and the boron nitride memristor in the probe station, we are integrating everything in real microchips. So we have made a multi-project wafer tape out in TSMC. This is the box containing the microchips, and this is the layout of the microchip. We have many things in this microchip because we have area. This is from 180 nanometer CMOS technology, so we can put many things here. Our true random number generator circuit is just this thing, which you can see here. Okay. So we are now testing this to see if we can produce, if we can provide a custom solution for this true random number generation. So the main conclusions of my work is that 2D materials have started to be used by the semiconductor, let's say microelectronics industry. State-of-the-art CVD-grown 2D materials contain too many defects, which prevent their use in transistors, especially boron nitride cannot be used as a reliable gate dielectric so far, but they can be used to fabricate memristors, as I have shown in this study. And if you are interested on knowing more about our work, you can check our recent articles. And if you think you could fit for my group and are interested on working with us in this field, we have some postdoctoral fellowships available in this website. And we also have some PhD positions available. And our campus also offers excellent facilities and is very beautiful, so you can also enjoy it. And that's everything I have to present for today. Thank you very much for your time, and if you have any question, I will be happy to answer.
Thank you, Professor Mario, for your very informative talks. Now, the floor is open for the questions. So now I request to all the participants, please unmute yourself and then you can interact with your MDL.
Thank you very much, sir, for your informative talk. I have a few queries. May I ask?
Yeah, of course. Go ahead.
Yes, sir. My first query is that catalytic substrate is feasible in case of graphene, as you have mentioned that. But generally we are not preferring for other 2D materials growth. So is there any specific reason for that?
Well, here in this slide, you can show the family of 2D materials. Okay.
Yes.
We have many 2D materials that have been so far discovered mainly by mechanical exfoliation. Some of these materials can be grown by chemical vapor deposition.
Yes,
And the most popular are graphene, some which is a conductive material. Some others are transition metal dechalcogenides like molybdenum disulfide. They can also be grown by CVD. In my case, I use hexagonal boron nitride, which is an insulator, has a wider band gap.
yes,
Each of them use different precursors and also different catalytic substrates. Even for the same material, you can use different catalytic substrates. Actually, for boron nitride, the growth has been demonstrated on copper, nickel, iron, and platinum. So you need some intrinsic properties from the substrate. For 2D semiconductors, normally sapphire or silicon oxide are more employed.
yes, sir.
So I'm not a very big expert on these chemical reactions, but I think I take the ones that give the best performance in the literature and I go for them, which for my material so far is single crystal copper gives the best result.
Yes, sir. Thank you, sir, for your answer. And my next question is related to the removal of boron nitride. As you have mentioned that first you will deposit the boron nitride by chemical method on the whole substrate. For contact, during the contact formation, you have removed the or etch out the particular boron nitride from the substrate for a direct contact of a metal on that semiconducting channel. So which technique we can completely remove the 2D material? Any chemical technique you have used for the formation of metal contact on 2D semiconducting material?
Well,
In the previous
you
slide, you have
transfer
shown that.
when you
No,
transfer
sir.
the 2D material on your target substrate and you want to fabricate the device, normally you use a polymer on top of your material.
No, sir. I'm not asking related to this particular slide. My question is related to the, I think, previous slide where you have formed the contact.
Yeah. So for the electrical contact between the 2D material and the electrode of the device, actually that is a whole science. That is one of the main problems hindering the fabrication of transistors, because that limits the mobility of the whole transistor. And this is an excellent question. There are many recent articles. There is a very famous in Nature from MIT and TSMC that deals with this and achieve record mobility. Some people claim in the past that using contact from the edge of the 2D material, putting the contact here instead here, produces lateral bonding, and then this reduces the resistance. This was a science paper. And some other studies investigate different materials like iridium or others. So basically, I think the engineering of the junction is a very important problem. I know these mainly two strategies, and I'm not very expert on the best combination because I work on Memristors.
Yes, sir. My another question is related to the growth time. As you have shown that when we take the particular duration, so we will get the single crystals of boron nitride. Yeah, on this slide, 30 minutes. As we have taken the growth time for 30 minutes, we will get the single crystals. After that, these submerge as the size of these crystal enhances. And when we consider the growth time as 2 hours, so we will get the complete film. So it is right, but my question is that if we are increasing the growth time, then the super saturation will occur there, or the contamination will increase, because in case
the main
of in case of a graphene, we are using only carbon, but in case of TMD growth, we are using molybdenum and sulfur. Both precursors are there actually. So if we are enhancing the growth time, then the sulfur supersaturation will enhances there. That will further enhance the contamination.
Well, if you have a clean environment inside your furnace, the main effect of the extending the growth time will be an increase of the thickness of your material. The first layer that you grow is normally faster than the rest because the first has seized the catalytic substrate and the reaction is boosted. After that, growing more to the material on the first layer, the speed is reduced. So if the environment is clean, and this is why you have the pumps, in principle, you may see thickness increase, maybe some multi-layer islands if you have some local defects in the first layer. But in principle, you should not have aggregates of molecules that produce some degree of contamination, because the atoms that you have are exactly the ones from the material you want to grow, and they will bond always in this 2D arrangement. So I will say, of course, if you increase the time, you have more probabilities of being increasing the contamination. But I think the alignment of the bonding, it will be in this 2D lattice.
Yes, sir. Yes. Thank you very much, sir, for your answers. Thank you very much.
Thank you.
Is there any participant to ask?
Yes, hello.
Hello.
Can you hear me?
Please, Ramesh and
Yes.
Anirudh.
Yes,
please,
yes. I'm
please one by
Ramesh,
one.
and thank you very much, Dr. Lanza, for nice presentation. Few years back, I have measured the RTN on HFO2 using STM in Professor Pei's lab in SUTD. And so I have a couple of questions on that. In slide number 25, you have shown the RTN. But my question is, what are the origin of these RTNs, whether it's a boron vacancy or nitrogen vacancies, or what are the origin, or what is the origin of this?
Yes. Actually, I didn't explain in the presentation that these current fluctuations are produced by electron trapping and detrapping, charge trapping or detrapping in the native defects of the material. Okay.
Mm-hmm.
So what are these defects? That's the main question, right? What are these defects?
Yes, yes.
If we check the images, okay, this is something that actually it is very difficult to know, because what you see in this image, all the information that we have about these things is from this image, from this type of images, from the cross-sectional TEM. So what you see here, because let me say, if you do nanochemical maps of this thing, it's really difficult. The top view TEM images, some scientists have published chemical images with atomic scale resolution in single layer top view. But here we have multi-layer and cross-sectional view. So you have this thing that we are seeing here is 40 nanometer thick, 40 nanometers. So there are, in one single position, there are atoms of boron, nitrogen, and probably also from the electrodes, okay? So that's the first difficulty, why the nanochemical analyses are so difficult in this type of sample. Second, nobody else has reported chemical information of these things with really atomic scale resolution. My group has reported, one of the few, cross-sectional ELS in one point where we can see the signals fluctuating depending on the thickness, okay? But real atomic scale is very difficult, and nobody has ever done. We are trying now with the super machines here in KAUST, so we are working on this. So when you do this, you don't know very well which is the chemical composition of these things. Anyway, as I mentioned, if you here there may be boron, nitrogen, and atoms from the electrodes. But if you see closer here, and this is a TEM image. In a TEM image, the atoms are black, and the bright signals are the spaces between the atoms that they arrive to the photodetector, to the electron detector. So here, what we are seeing is gray color everywhere, okay? Which means that these bright places are not bright anymore. There are atoms there. So we have atoms that are not where they should be. They are not in a 2D lattice, but they also locate in between the layers, okay? So basically, these are interstitial atoms. This is not a boron vacancy. This is not because if it will be a boron vacancy, we will see a black line that is interrupted by a bright color and that then continues. That means boron vacancy. Here, what we have, maybe we have also boron vacancies, but we definitely have atoms in the bright areas. So we have atoms that have moved. I think after long discussions, recently we have came up with the conclusion that the most common defects here are interstitial atoms, that they could be borons atoms that they have formed a vacancy, but that they have gone in between two planes. This is not just a boron atom that leaves the material. It stays somewhere there. And I think this is playing an important role. In my team right now, we are doing this structure simulated, many different defective structures simulated with atomic scale simulations. Like this structure is completely amorphous, but we are also trying to simulate, for example, this type of structure and see what happens. I believe this type of interstitial atoms are behind the random telegraph noise signals. Although I have to say, the random telegraph noise signal that fluctuates between two states is normally one defect in which there is charge trapping and detrapping. So knowing which one it is impossible.
Okay. Okay, I have another question.
I have to say, especially in such a large device, if you do STM in one single point, most probably you will have narrow, and you can even go and scan one single point. Actually, there is a very interesting paper from Professor Deja Kimbande in Nature Nanotechnology or Nature Electronics that uses STM to observe non-volatile bipolar resistive switching. This works called atom restore. But in this case, it's just charge trapping and detrapping. What he's doing is moving one atom.
Yes. Can I ask one more question?
Yeah.
Yeah. So in the slide 27, you showed the AFM images of grains, grain boundaries, and traps. So do you see a different telegraphic noise if you measure the RTN in the grain and RTN in the grain boundary, for example, and RTN in the location where grain boundaries meet together?
Yes.
So do you see any differences in the RTNs you measure?
No, I didn't
Because the
measure
trap
it here.
concentration is completely different, right?
Yeah. And I didn't measure here. I only measured here. Because these grain boundaries, in many cases, if you analyze very large areas, you just see higher currents. This is nanoamps, but for 4 volts, if you put the tip here, you just see higher currents. So probably it's not just one defect, it's like a big cluster, as you mentioned.
That, I mean, in the same slide, you mentioned you have applied 4 volts for the tip. So then the question comes, what is the breakdown voltage in this case?
Oh, yes. If you apply a ramp voltage stress in one of these little points for this type of boron nitride, which for this experiment was 6 nanometer thick, you still need a little bit more. Think on something. The breakdown voltage in conductive AFM is much higher than in normal devices, okay? So actually here I need 4 volts to see random telegraph noise, while in the device I need 70 millivolts. Also, the material of the tip is platinum, in the other case is silver.
Okay. Okay, thank you. Thank you so much.
Thank you.
Yeah, thank you, Professor Ramesh. Now, Anirudh, please.
Yeah, thank you. Can you hear me?
Yes.
Yeah, hi, Prof. Lanza. I'm Anirudh. I'm doing my PhD in 2D material reliability from Prof. Pay Group. Firstly, I would like to thank you for the very nice presentation.
Yeah.
I have I have a doubt in slide 29. You did mention there that the RTN noise was quite low, so we use a few methods to actually increase the frequency of the RTN noise. I just wanted to know over a period of time, did you test in some way to see if the frequency of the noise was increasing or decreasing?
You mean the random telegraph noise?
Yes, I just meant the frequency of the random telegraph noise. Was it consistent or over a period of time, was it increasing or?
Ah, you mean the frequency of this random telegraph noise?
Yes.
Usually there is a distribution of the switching times, actually switching up and switching down, which are normally called capture time and emission time. You have this here, okay? And there is a distribution, okay? There are some cases it's very fast, some cases it's slower. So this trace that you see here is the second longest ever reported. The longest is like 1 hour and a half, and this is like 1 hour. Okay, the longest is for hafnium oxide, is for boron nitride. It depends on how you do. Normally, people show you 10 seconds, 3 seconds, 20 seconds. So this is already quite long if you compare with other studies. The main problem actually is not that the frequency of the switches changes, because this is why you have you can match this with the circuit. The problem, in fact, is that this may eventually stop switching, or that the background current increases. Well, that is also something can be corrected by changing the comparison value according to the background increase. But sometimes this stop switches. You see here stops for some time, then it switches again, then here stops up for some time, switches again. But eventually it stops, you know. So that is the biggest problem of this type of circuits, okay? So other studies recommend to use another source of variability, like set voltage, reset voltage, or switch time, you know, and those RTN based on those true random number generators based on RTN of Memristors. Some people criticize more. So it depends. We just need to demonstrate. So this is what we are working on.
Understood. Understood. Thank you.
Yeah, thank you, Professor Lanza. So, is there any questions from the audience?
Yes, one more question. Sorry. Professor Lanza, why not consider this graph with multiple states? In fact, if you consider the graph C, for example, you have 1, 2, 3, 4 states, in fact, right? So did you consider that also? or going from 2 states to an anomalous signal, for example?
Yes, yes. There are, in this article, in the supplementary information file, you can find plots of multi-level random telegraph noise, which are formed by the coexistence of more than one type of defect. So you can have 4, 6, 8 states.
Yes.
This is something exists and has been also used.
Okay, okay, yeah.
Okay, I think we
Good
only take the
afternoon,
last
sir.
question from the Shruti. Yes, Shruti, please ask.
Yes, sir. Good afternoon, sir. I have a doubt, like how much difficult it is to deposit the hexaboron nitride using the CVD as compared to the TMD material and graphene.
The transfer of the 2D material is its big advantage compared to other 2D materials, because this is an insulator. In microelectronics, you don't use insulators that are so thin. The thickness of one layer is 0.33 nanometer. And normally, when we use dielectrics in devices, capacitors, memristors, transistors, at least we have 2 nanometers. So I work with 6 nanometer thick boron nitride, and when I use monolayer, it cracks super easily. But when I use multi-layer, it doesn't crack. So working with multi-layer is much easier at the wafer scale, and I am completely convinced that the first devices of high integration density will be done with multi-layer 2D materials, not with monolayer 2D materials. However, for graphene and semiconductors, you need thinner is better. So there is a trade-off. The thinner, the better for electrical properties for semiconductors and conductors. However, the thinner, the easier you break it. So it is a trade-off.
Yeah, thank you, Professor Lanza. So we will not take any more questions because time is running now. So thank you so much again for your giving the time for our IEEE community and share your
Thank you.
research with us.
Thank
We
you
are
very
very
much.
grateful to your accepting our invitations. Hope we will meet in the December in ISC Bangalore conference.
Yes,
So thank you
yes.
so much.
Hope to see more Indian friends there. Thank you very much.
Yeah. Thank you, Professor Lanza. Thank you so much.
Thank you. Bye.
Bye. Bye.